Hello, everyone. Welcome to today's live broadcast, Increase ESI-MS Throughput up to 10 times by multi-segment injection. I am Brenda Kelly-Kim of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by SciEx. SciEx helps to improve the world we live in by enabling scientists and laboratory analysts to find answers to the complex analytical challenges they face. For more information, please visit sciex.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click the support button at the top right of your presentation window or submit your problem to the green Q&A button lower left. I would now like to introduce today's speaker, John Hudson, Adjunct Professor at the University of Regina in Regina, Saskatchewan, Canada, and a staff scientist with SciEx. Before I turn it over to John for his presentation, please respond to the polling question, which will come up on your screen. This will help John get to know his audience. John will now begin his presentation. Thank you for your answers to the polling question.
Greetings, everyone, and thank you very much for joining this webinar this morning. This webinar focuses on increasing throughput in electrospray ionization mass spec using a technique called multi-segment injection. Now, I've been working in separation science for quite a long time, and I got interested in capillary electrophoresis around 1993 while working as a toxicologist. As a toxicologist, I was analyzing drugs and poisons for the Royal Canadian Mounted Police forensic system. And since that time, I've spent most of my time on the integration of capillary electrophoresis with mass spectrometry. CE has made the analysis of polar drugs and their metabolites no longer much of a challenge to toxicologists, and it's an ideal fit with electrospray ionization mass spec. Since that time, CE has made its way into a demanding regulatory environment of biopharma and quality assurance, quality control. Its use speaks volumes about the technique and its dedicated scientists who are using it to deal with analytical challenges ranging from the routine to the exotic. Today, I'd like to go over 3 sections in my talk. The first one is to discuss conventional methods and optimizations using standalone CE in an attempt to decrease analysis time and thus increase throughput. The second part, I'd like to talk about CESI-MS, which can provide a very effective tool in increasing analysis speed and decreasing the total time required. And then I have a couple of case examples that I'd like to show you using methamphetamine and its metabolite amphetamine as an example. So what tools are available for decreasing analysis time? Back in about 10 years ago now, a group over in Switzerland, Jean-Luc Bouthet's group, published a couple of papers that I bring to your attention. Now, these papers were used in standalone CE, that is not connected to mass spectrometry, to look at the various ways that one can use capillary electrophoresis to speed up analysis. And this was an excellent study that I'd like to show you now. Some of the points, there were 5 considerations actually here. To increase speed, there were simple things that were done, such as use a shorter capillary or increase the voltage across the capillary, the field strength. With that combination, you could speed up your analysis. Of course, that would depend on the resolution that existed in your separation. You could also change the pH or coat the surface of the capillary to increase the EOF, which is the intrinsic flow within the capillary. This is used also to stabilize migration times in CE where needed. Another thing that you could do was to inject from the short side of the capillary if you had an adequate separation of the analytes. This is commonly used in chiral standalone CE. This is really not possible, of course, in CESI or CEMS because there is no outlet end of the capillary. Again, if the separation of the analyte is adequate, you can also speed things up by applying pressure to the inlet side of the capillary electrophoresis instrument. In other words, if the separation has been achieved, you can simply push everything to your detector, whether it be a UV detector or ultimately a mass spec detector. Multiple segment injections can also be used in standalone CE in many applications. And this slide shows a practical example from a few years ago when I was working at the Royal Canadian Mounted Police Lab. And this application was developed for a number of reasons. The application as shown involves multiple injections of drugs of abuse using internal standards in one run. And this was used to provide urgent information required by police officers involved in purchasing large quantities of street drugs such as cocaine, heroin, and MDMA or ecstasy. It employs the use of an internal standard, which is very important, and the calculation of peak area ratios. The peak area ratio is that of the drug of abuse to the internal standard. Duplicate injections of the standards of the standard of interest, like heroin, for example, with the internal standard were compared to the case samples. And using that ratio, we were able to quickly calculate the percentage of drug in the powder that would have been submitted. Now, why is that important? Well, it's important because this is a safety issue for the investigating officer. If he buys a small sample of drug and then goes back to try to buy a larger quantity, it's very important to have accurate information so that the trafficker does not realize that this is a buy, and that information is critical to the safety of the officer. The work of and the use of multiple injection techniques has recently resurfaced in the exciting area of metabolomics. And the work shown in this slide was done by Philip Britz-McGibbon's group in Hamilton, Ontario, Canada. And for those starting to apply this technique, this is a very good paper, a very good starting point. I also thank Philip for allowing me to use the slide and the graphic that I'm going to show next. So in multiple segment injections, the samples are injected sequentially onto the capillary, and they're separated by means of a spacer. And in this case, the spacer is usually an injection of the background electrolyte. There may be some rinsing and cleaning steps at the beginning to ensure that the internal surface of the capillary is uniform and allows good reproducibility. The volume of the spacer is determined in method development for the separation at hand. The separation is done using an applied voltage across the capillary, usually 25 kV up to 30 kV. And I use 30 kV, and you'll see that in the conditions, which I'll show later. As a sort of a proof of principle as to whether multiple segment injections would work, at that time I was working in some metabolomics experiments, and I did a multi-segment injection shown here, which involved the injection of 8 samples in each run. So in 2 runs, I was able to get a full calibration curve, and these are single point calibrations. And also, I also included, as you'll see on the right-hand side, a urine sample which was volunteer urine. Of course, that was my urine, in order to calculate the amount of arginine that was spiked into synthetic urine. So this was really the spark that encouraged me to go and have a look at a further verification of this type of technique. Now let's talk a little bit, first of all, about the detection and separation mechanism that we use. And I'd like to provide a little bit of detail on the CESI, which is this very low-flow, high-sensitivity technique. Now the acronym CESI describes the integration of CE with electrospray ionization into a single dynamic process within the same device. Now what does that mean? It means that the sprayer itself is built into the separation capillary, and as such, there are no connections involved to have to consider things such as dead volume or connection problems. The end of the sprayer tip is part of the capillary and is precisely and chemically engineered to micrometer tolerances. The other point is that the internal diameter is 30 microns, 30 micrometers. This is not modified as in nano-LC, where most of the capillaries are pulled to a very fine point. The sprayer tip is not modified at all, and this helps to eliminate potential clogging of the tip. The electrical connection is made between the ESI needle through a static conductive liquid, through the wall of the capillary, sprayer tip, to the background electrolyte inside the capillary itself. Some of the intrinsic properties of CESI also apply to capillary electrophoresis as well. Charged and polar molecules can be analyzed without derivatization. It results in a lot of labor-intensive time saved. The low flow rates, these low flow rates are very low. They can be under 10 nanoliters per minute. And as a result, you're now working in the mass-sensitive region versus the concentration-sensitive region. And there is much better sensitivity down at those low flows, along with improved ionization and much lower electrospray voltages and all the good things that go along with that, such as reduced ion suppression, reduced matrix effects. So at those low flows, the sensitivity is almost spectacular. The sampling requirements in CE are extremely low. We're talking about nanoliter volumes injected, which corresponds to low femtograms on the capillary, and that is, of course, before it gets into the mass spec. It's difficult to estimate how much actually gets into the mass spec, of course. In order to get those sample from those low volumes, low microliter volumes, in order to sample nanoliters from microliters, it's important to have a mechanism, a vial that you can inject from. And shown here is a new nanovial, which is unique to SciEx instruments. This is a low volume vial available, which allows sampling down to a few microliters. And the vials are validated to 5 microliters, but it is possible to get down to 1 microliter, depending on the sample itself, such as viscosity. A couple of other properties of CESI. It's essentially non-destructive in that you're injecting nanoliter quantities from microliter amounts. So basically, your factor is the order of 1,000. You hardly use any sample at all. The separation options include the pressure assistance at any stage in the separation to shorten the overall run times. And by that I mean, once the separation is done, you can simply use pressure at the inlet, and I've mentioned that before, to push everything off. Injection can also be done using pressure or using voltage. In this slide, I just wanted to reiterate to the CE users out there that it's important to consider using voltage injection or electrokinetic injection in your processes. And there are many reasons for this. I want to describe at this point that both injection techniques. On the right-hand side, the hydrodynamic detection simply means injection by pressure of a fluid by pressure or possibly by vacuum. Vacuum, of course, is not possible in mass spectrometry, CESI-MS. So you can inject using pressure, and this results in a representative sample being introduced to the capillary. And this is similar to gas chromatography and liquid chromatography sample introduction. However, in capillary electrophoresis and in CESI, the injection using voltage is also possible, and this differs from GC or LC where that can't be done. So a voltage or electrokinetic injection on the left-hand side is essentially the result of turning on the voltage and migrating the ions of interest onto the capillary. And this has a number of effects. It is really a built-in pre-concentration effect. And also what it does is it discriminates between which ions you want to get onto the capillary. So for example, if you want cations to get on, you would have the mass spec as essentially your negative electrode on the other end. And this is important, especially if one has very dirty samples, so that you can leave behind, in this case, you'd leave behind acidic material and neutral material and only migrate cations of interest such as nitrogenous bases which have been protonated. The approach used in MSI work, multi-segment injection, is really a combination of a pressure injection along with a method called transient isotachophoresis. I won't go into what that is, simply to say that you dissolve your samples in an electrolyte, which allows a very precise focusing to happen of your sample analytes. Those samples are reconstituted in 25 millimolar ammonium acetate, and each segment is injected, followed by the spacer. The CESI itself is very easy to set up. What we've shown here is a schematic showing the consumable cartridge arrangement where the sprayer tip is as shown. I'm just going to draw an arrow to the sprayer tip. Hope everybody can see that. The sprayer is enclosed in a retractable tip, and that's all part of the same consumable. And that sprayer tip is then inserted into an adapter into the mass spec, and the adapter is specific to that particular mass spec. This slide shows the integration of the solution, and in this case, the CESI 1000 Plus instrument is interfaced with a SciAx 5600 triple top. And this is, of course, used via a nano source. In this case, I think it's a NanoFlow 3, and that makes the connection with the CESI. As a little break and to provide us with some more information, I was wondering whether you would be able to do one more polling question for me. And this is, what are the average number of samples my lab runs per week? I'll give you a couple of seconds to do this. I find this always very interesting to find out what people do. So just give you a couple of seconds to check it in. And I believe we're going to quickly display the results. So we have lots of people out there doing lots of samples per week. Very encouraging. Thank you very much for doing that. So for my case study that I did, I selected a drug that's very prominent in the news. This is methamphetamine, which is also known as crystal meth. And you can just about turn on the news any night, and you'll hear a result, some news. describing the effect of methamphetamine, whether it be a car crash or a shooting or whatever. So this drug is in the news, and I decided that I would take a look at it along with its metabolite, amphetamine. And in this particular case study, the samples were spiked into synthetic urine samples. The extraction protocol is quite a simple extraction protocol, which is used widely around the world. It's a liquid-liquid extraction protocol, which can be used on either whole blood, urine, serum, plasma, oral fluids. The thing to note here is that the protocol shown suggests 1 mil. This can easily be scaled down to a few microliters, down to 20 microliters or even less, with no changes to the actual protocol itself. The final sample is dissolved in 100 microliters, so we are injecting nanoliters from 100 microliters, and you'll see a calculation at the end of my talk. The multi-segment injection CESI conditions are described here. The capillary itself was a 91 centimeter long capillary, as I mentioned before, with an internal diameter of 30 microns. And the other interesting part is in the sample preparation, where the samples were dissolved in 25 millimolar ammonium acetate, pH 4.4, for this isotachophoresis focusing step, which gives very sharp peaks and allows very high resolution. The samples were pressure injected with a spacer of about a 60-second 2 psi spacer, and the background electrolyte was 10% acetic acid, and we ran at 30 kV. Now, a lot of people look at the results and say, how does it actually work? How does the method actually work? So what I've done here is put this very busy slide in here, along with the graphic that I described earlier, simply to show you that the injection portion of the method, and it can be changed from one injection up to many injections, it shows a 2 psi 5-second sample introduction followed by a spacer. And this is done multiple times as per the graphic that I described earlier. And in this case, this is an 8-sample multi-segment injection in each run. Here's an example of spikes done in urine for the quantification of methamphetamine. So the slide shows 2 runs, an 8-sample on the left and a 6-sample on the right for single 10-point calibrations for methamphetamine. Now in each pane, the methamphetamine's on the top and the corresponding internal standard, which in this case was a D11 deuterated internal standard for, in this case, methamphetamine, that's on the bottom. So the calibration is done by doing a peak area ratio of the area of the methamphetamine on the top to the internal standard on the bottom. And I've also put in the order as well. Calibrations for methamphetamine were created from, in this case, triplicate MSI injections, which of course were sequential, and gave excellent linearity with R-squared values greater than 0.995. Interestingly, the polynomial or quadratic model gave values near unity. And I put that on there just because I could. So the metabolite of amphetamine also is shown here. And similarly, the calibration is calculated by using the area of the amphetamine to the area of the internal standard. And the linearity for the amphetamine was again very good as well. As further proof of principle, I decided I would extend this out, time permitting, and in my MSI further experiments, I was able to get out to 12 samples per run. And I simply used as an LOD and LOQ the low calibrator, or 1 nanogram per mil spiked into urine. And each segment injection introduces about just under 2 nanoliters from a total volume of 100 microliters. Again, this is really non-destructive sampling. And this corresponds to about 17 femtograms of the drug on the capillary from the 1 nanogram per mil sample, the sample segment. And this shows this again was triplicate injections, showing the linearity of the amphetamine on the left and methamphetamine on the right. So my concluding remarks are very general. Using multi-segment injections, CESI-MS, it's clear that we can increase throughput significantly using this particular technique. The quantification of the case study analytes were all done with very good linearity, over 3 orders of magnitude. If you look at the total times involved in one run, this would include capillary rinses, injection of samples, separation, ramp down time, and movement, of course, of the sampling mechanism within the instrument. So a total of samples can easily be analyzed in 40 minutes, or about 4 minutes per sample, just under 4 minutes per sample. And this is almost a 10x improvement over a run of 40 minutes, which also includes all those steps. Time permitting, I'm continuing work on this to optimize the method and to further increase throughput. So I'd now like to turn this back over, and I'd like to thank everybody first for attending the webinar, and I'd like to turn it back over to Brenda for a couple more questions.
Thank you, John, for that informative presentation. Lots of good information there. Before we have our audience questions, I would just like to ask them once again to kindly take a moment to respond to the polling question that will be coming up on the screen. And while they're doing that and that's going on, I'll be reminding you how to submit questions. Questions can be submitted by typing them in the green Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many of your questions as we can. And we do have one question right up top. One of our audience members asked, what is the flow difference, John, between CEMS and CESI-MS?
And I'm assuming that you're referring to, when you say CEMS, you're referring to sheath flow CEMS. The comparison is an order of magnitude. For example, I did a lot of sheath liquid work years ago, and we were using makeup flows and column flows that were around 2 microliters per minute. In CESI, the flows, as I indicated in the slides, were down in low nanoliters per minute, typically around 10 or 15 nanoliters per minute, depending on the type of capillary used and the type of separation done.
Awesome. Thank you. We do actually have another question. With nano-LC-MS, our lab also injects from a few microliters. What is unique about your nanovials?
Well, the nanovial has been designed to allow the introduction of small microliter quantities and to allow the electrode and the capillary to be positioned accurately in the liquid and to provide both the electrokinetic and a voltage injection. So that's quite unique. Also, it's been designed to go into the sample trays as a pair to ensure precise alignment with the mechanism in the instrument.
Great. We have another question. Once the Cal curve has been injected, are your unknown samples also run in multi-segment or individually?
Could you repeat that one for me?
Our audience member asks, once the Cal curve has been injected, are your unknown samples also run in multi-segment, or are they run individually?
Yes, the unknown samples are run simply as another sample and can be inserted anywhere in the multi-segment injection area. For example, you could bracket your unknown samples with calibrators on either side or blanks and internal standard. Remember that the spacer itself is really a blank, which will indicate whether there's any carryover between between samples. So there's a built-in blank as well. So that, to reiterate the answer to your question, you can put your analytes anywhere at the beginning or end and intersperse them with decalibrators.
Thank you for that. Our next question, how much sample volume is minimally needed in the nanovial for a reliable injection?
Well, the nanovial was validated down to 5 microliters. And to go any lower, it really depends, again, on the solution that you're using, the viscosity, whether you can actually get it down and positioned in the bottom of the nanovial. To date, most samples are dissolved in a fairly dilute background electrolyte and are easily positioned with a long pipette tip into the bottom of the nanovial.
Great. Well, that is all the time we have for questions today. I do want to thank our audience for attending and for their great input. I also want to thank John for his presentation and our sponsor, SciEx, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through May of 2016. You'll receive an email from LabRoots alerting you when this webcast will be available for replay. And we invite you to forward that announcement to your colleagues who may have missed today's live event. Thank you for joining us. We hope to see you next time. Goodbye.